All right, now we're going to take a little, today, we're going to take a little detour. Our author uses concepts from linear temporal logic, and we're going to delve into this, to these concepts a little bit deeper than our author does, and we're going to go through a paper that actually one of your colleagues from a previous generation, someone who was in this class, and I, David Vega, and I collaborated to do some research to, and we got this material that we're going to learn today. Basically what we've done is all of you in this room have taken the formal methods and discrete structures, and we know that system of equational logic. And then that handout that I gave you last time has the propositional calculus theorems from that course. But then in the second half of that packet, there are a number of there's a set of theorems that are the theorems and axioms for linear temporal logic. And because we already have the tools for for the equational system for propositional calculus, what we've done is we've extended the theory using our logic system that we learned in formal methods to linear temporal logic. And so so that's what we're going to do today. So here's the thing, you guys. What happens is in concurrent programming, frequently the programs that are written are not designed to terminate. They're designed to loop forever. So we can't use the Hoare triple because the Hoare triple says what has to be true when statement S terminates. So instead of using the Hoare triple, we have to prove that certain properties exist. And what are the three things that we always want our solution to the critical section problem to have? What are the three ones? Well, first one is what? We want to have mutual exclusion. Second one is no deadlock. And the third one is what? So no starvation. So the tools of linear temporal logic help us to reason about the correctness of programs that typically don't terminate, and that and where we want to prove these properties. Okay. So the title of our paper, the paper's online. The title of our paper is An Equational Deductive System for Linear Temporal Logic, and this parentheses student means this is the student edition, and the student edition has, for some of the proofs and the theorems, it has exercise for the student. So those will be the ones that you will prove. Yeah.
Are we going to just prove, when it comes to proving deadlock and starvation, can we just prove starvation and then know that also means?
Yeah, that's a good, actually, because starvation is harder to prove than deadlock, I might give you an assignment to prove deadlock just because, prove it's deadlock free just because it's easier.
Okay.
So you should appreciate that. But anyway, yeah. So if we, yeah, but the starvation is the hard one, and if you prove that it's starvation free, then you have proved that it's deadlock free because we saw how that worked before. Okay. So now, here is how the system works. Now we're going to go through this. Do you have your equation sheets that I gave you last time? You should probably get them out because we're going to prove some theorems. So, in fact, we might even go around the room and ask. Yeah. So, here we go. First of all, there's a precedence table. All right? And some of these operators you are familiar with. The three equivalents, implies, follows from, conjunction, disjunction. Are you with me on that? Those are all the ones we've had before. And this one up here, this unary one, not. But now, what are these ones that you haven't seen before? This circle, that's called next. This diamond, that's called eventually. And this square, that's called always. And these are unary operators. So these are new unary operators that we're going to learn about today. Then we have the U and the W. The U, the script U, we say that's a letter, an abbreviation for until. Are you with me? So the U is until, the W is wait. So we have next, always, next, eventually, always for the unaries, and then until and wait for the binary. Does everybody see? And so we're going to take a look at the properties of these new ones. And they are added. They're added onto the conjunction and disjunction and implies and the other ones that we already know. All right. Now, to start off, we need to know what is the definition of a model. A model, sigma, is an infinite sequence of the form S0, S1, S2, and so on. Now, here's the thing, you guys. Remember whenever we analyzed our concurrent programs and we had a state transition diagram, and we said if it might be possible for two different statements to execute, one in each process, and depending on which one executed, we go to one state or another one. Are you with me? So that sequence of states is what this represents. S0 is one state, S1 is the next state, S2 is the next state, and so on. So this represents the program executing in time, and as the state changes, then a Boolean expression, the value of a Boolean expression might change along with the state. So here is an example of a state, or of a model. Okay, so sigma, see, for example, you might have something like, you might have a program in which x is a variable, and maybe the values of x start out, maybe x starts off at 8, and then it goes to 9 and 10 and 11 and 12. Then as the value of x changes, as the computation progresses, this expression, x is greater than or equal to 10, will also change. So is everybody with me on that? And do you see what happens is, at state s sub 0, x is greater than or equal to 10 is false. At S1, it's false, but then at S2, it's true, and at S3, it's true, and so on. Are you with me? So you see what that physically represents, the execution of a program, and an expression can have its truth value change as the computation evolves and as those states go on. Is everybody good on that? Okay, so now, to explain what these operators mean, these temporal operators mean, we have this vertical bar equals thing, right? And now, what is sigma? Let's go. What did we say sigma was? Sigma was a sequence of what? Of states, a sequence of states. And then J is one of those. All right? So like here, sigma is the sequence of states, S0, S1, S2, S3, S4. So this is a sequence of states S sub J. Are you with me? So J is one of these, is one of the subscripts there. Are you with me on that? So this means that the expression P holds that position J in a sequence sigma. So let's do an example of this. So here is our previous sequence. Now do you see then that the fact that in state S3, x is greater than or equal to 10 holds? The way we say that is sigma comma 3, close parentheses, holds at state x greater than or equal to 10. Or sorry, x is greater than or equal to 10 holds at state 3 in sigma. Are you with me? X is greater than or equal to 10, that's the P. So we say that state holds at position 3 in this sequence sigma. Is everybody clear on that? Another way to say it is you can say satisfy. If you want, you have to read it from right to left. If you want to read it from left to right, you can say satisfies. You can say sigma comma 3 satisfies x is greater than or equal to 10. You can use the word satisfies if you want to. Now, the first operator that we're going to learn is the next operator, that's the circle. And it's a prefix operator. And check it out. the semantics of the unary prefix operator is, now what do we say? Next P holds at position J if and only if what? Well, close but no cigar. Next P holds at position J if what? P holds at position J plus 1. Now, are you with me on that? See, does everybody see how that means? How that works? Okay, so now look at this. Here's an example. So suppose x is the value of x in states S0, S1, etc. are 8, 9, 10, 11, 12, 13, and 14. And we have this expression, 10 is less than or equal to x is less than 13. Now, do you see how the second row, is everybody with me on the second row there? Okay, it's false, false, true, 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 false, false, right? Because like in state S3, 11, 10 is less than or equal to 11 is less than 13, yeah? And now check it out, you guys. So false, false, true, 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 false, false, that's 10 is less than or equal to x is less than 13. But what about next 10 is less than or equal to x is less than 13? Why is that true in state S1? Well, why is next P true at state 1, at state S1? Not because P is true at state 1, but because
P is true at state
2. Yeah, at 2, right. So does everybody see that? Is everybody with me on the notation there? It's okay. All right, so that's the meaning of next. And why is it true here? Why is it true in state S2? Because it's true in S3. But what about this? It's true here because it's true here, right? Does everybody see that that's what, is everybody with me on what next means? Okay? And here, false, false, right? Are we good? So that's what that means. Now, so that's our unary operator. Now the next one is called until. Now you guys, in the English use of the word until, what is, you know, I'm going to be hungry until I get In-N-Out burger. So what does that mean? Yeah, something is going to be true until something happens, right? So there's two. So the semantics of the binary infix operator U for until is the following. P until Q is true. P until Q holds at sigma J, at position J, it holds. If and only if what? So now when I say I'm hungry until I'm going to get an In-N-Out burger, what does that mean? That means there exists a what? I'm going to be hungry until I get the burger. So what, first of all, it means that what? There is going to be a time in which I do get the burger, the In-N-Out burger, right? So there exists a k. Now why would be k greater than or equal to j? So that's in the future. Are you with me if we're talking about time? Is everybody clear on this? Okay. So there exists a k in the future. Actually, the future may include, this is greater than or equal to, so the future may include what? May include now. Do you see what I'm saying? In the now or in the future. Are you with me? There exists a k, now or in the future, such that what? Q holds when? No. There exists a k in the future now, or there exists a k in the future such that Q holds when? At that point in the future, okay? And furthermore, what? Yes, P holds everywhere up until that. Now, does everybody see? Can everybody read this? Okay, this is just a nested quantification, which is what we've done in formal methods a lot.
Can you explain the segment inner quantification one more time? So
Okay,
holds.
P holds. So not only does Q hold in the future at time k, but for all times in between now and k. See, J. What is J? J is all I. J is all states I up to not including k, up to but not including k, and p holds at that I. Now, do you see how that works, the meaning of that? That's the meaning. And furthermore, furthermore, does p have to hold at k? No, it doesn't. But what has to hold at k? Q has to hold at k. P can stop holding at k and we're still fine. It still fits the definition. Is everybody clear on that? Now, does everybody understand this? This is a nice big concept. It's until. All right? So let's do an example. Okay, so let's go around the room maybe. Who wants to start? Here is, let's suppose that x evolves like this. -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. And y evolves like this. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So x is going up, y is going down. Now, can you tell me what are the truth values of 0 less than x less than y? So in which of these things is x between 0 and y? Which ones are x between 0 and y? S what to S what? Greater than, strictly greater than. S2 to S4, is that right? So what will it be? What will the letters be? False, false. Wait, false, 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 or
Oh, true.
false, false, what? True, true, false, false, false. Is everybody with me? False, false, true, 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 false, false, false. Are you with me? Is everybody clear on that? Now what about the letters for 2 less than or equal to y less than 5? 2, so what will that be? False, false, false. Is that what you said? True, true, true. And then what? And false the rest. Okay, so it's going to be false, false, false. Oh, wait.
It's less than 5.
Yeah, so
It's less than 5.
It should be true at 2, 3, 4.
No, you're looking at x.
Oh, that's right. Wow, okay.
Oh, yeah, you're right. I hope this is
Oh,
right.
that's right.
It
Yeah.
is right.
Yeah,
Okay,
yeah.
so false, 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 true, 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 false, false. Is everybody clear? All right, now here comes our big deal. Here comes our big deal. What's the value of 0 is less than x is less than y until 2 is less than or equal to y is less than 5? This has a truth value at S0, at S1, at S2, at S3. Are you with me? It has a truth value at each one of these spots. And what is it? Here's my question. Do you know what it is? Can you tell what it is at S0? This is the meaning. All right. So this is what? This is P until Q. It's X until, it's this until this. Okay. So my question is it true or false here? Who wants to, who thinks? Who wants to venture a hazard a guess, or not a guess, but a, is it true or false here at S0? You think it's false? It is. Now, why is that? Because it said it had to be what? I mean, in order for this to be true, what has to happen? This first one has to be what? It has to be true until this is true, right? But it's not. Does everybody see that? It's not true until 0 less than x less than 5. P is not true until Q is true, because it's false here and here. So it's not true until then.
Does it matter if S5 is true or not for 0 less than x less than y?
Yeah, that's a very good question. The question is, and notice this, less than K, not less than or equal to K.
I mean for
All right.
x, the row above it, the false there.
Oh, we're going to get to that.
Okay.
Good question. We're going to get that's an interesting question. We're going to get to that. Yeah, let's work our way up. Now, does everybody see that this is false? Okay, so what about the next one? Also false, because it's not, see, look, it's not true until then. What about the next one? True. Now it's true because it's true until, are you with me? And now what about the next one? True. And now what about the next one? And now what about the next one that you ask about? Now the question is, drum roll, what's this one? Now we have to analyze very carefully. What do you think? What we have to do is we're going to have to evaluate this whenever what is the case. We're going to have to figure out what this is in this particular case, where this is false and this is true. Say it again. It is an empty range. Yes, excellente. Did you hear that? It is an empty. So what is P until Q when K equals J? Because what happens is, does everybody see that there exists a K greater than or equal to J? Are you with me? So at this point, what's happening is K equals J. And what about Q? Q is what? True, and P is false. Does everybody see that that's what the question is? Are you with me? And you're right, it's going to be an empty. Do you remember the empty range rule?
Use the identity.
It's the identity of
For
the,
the case.
it's the identity of whatever the operation is. Okay, so look. So does everybody see that Q holds that K? That's true. Are you with me? Because we're here, our K is 5, right? So it's P until Q. So this is the true, that's the true here, okay? And P holds at K, that's false. Are you with me? So this one is true and this one is false. But now, what man told us was empty range rule. J is, what is this saying? 5 is less than or equal to what? 5 is less than 5. But now, so that's false, so that's the empty range. So what's the rule for the empty range? What's the operation for universal, for all?
Oh, for all. Sorry, I was looking at that one.
Yeah. It's and, is it not? Now, what is the identity of conjunction? P and what is P? True. Okay? So by the empty range rule, that's true. So that's why this is the empty range, so that's why that's true there. So, Shane, did that answer your question? So here, because of the empty range rule, this is false. That's why this is true. Even if this is true and this is false, that's why this is true.
I was wondering what would happen if P and Q were both true. I looked at the chart and saw that it is true.
Actually, it's even stronger than that. We can make a stronger statement than that. What is it going to be here? P until, what's it going to be here? Uh-oh. Yeah, because we said 0 is less than x is less than y until this. Is this going to be true or false?
True.
Oh, you say true. I heard another false, though. Anybody else? It is true. It doesn't matter what. In fact, what is this? What do we know about? What do we know about P until Q if Q? No, wait. P until Q if Q is true. At state K. Or
There's a false at S5, and that's not
Well, before when we were asking what is the value of P until Q at state 5, this is true because of this empty range rule.
Yeah, but the next one would
But but the thing of it is that if Q is true, it doesn't matter whether P is true or not, it's true. Are you with me on that? Because it's P until Q. If Q is true, it doesn't matter what. I know how to, look, let's go back to this one. Let's go back to this. Do you see that at state S5, P is false, but Q is true? Well, if P is false and Q is true, it's true. Same thing here. It's actually the exact same analysis. Are you with me? So here it's true, and now what about the rest? False, assuming these are false all the way out. It's not going to be. Is everybody clear? So it's actually the same analysis. Now our author, here's a slide 4.8 from our textbook. Here he has A until B, and he has I kind of don't like the way he does his things he doesn't do it J in the middle, but anyway, I quibble with his presentation here, but you see what happens, what he's saying is that here A until B is true. A is true, so this one, notice that this B is bold, and this curve is bold down here, and this A is not bold, and this top curve is not bold. So this top curve represents A, and this bottom curve represents B. The bold one represents B, and the unbold one represents A. And do you see, what he's saying is that A is true until B is true. So you see, even though B is not true now, A is true until B is true. That's how he illustrates A until B graphically. Okay? Now, the next operator is the eventually operator. That's this diamond. And now, what does eventually mean? It's going to happen sometime in the future. You know, like, eventually you'll get a job. Sometime in the future, you'll get a job. Right? So it's going to happen. So what's the meaning of, what's the meaning? Eventually P holds at time J if and only if what? There exists a what? A time K in the future such that what? P holds. So look, here's X is 1, 2, 3, 4, 5, 6, 7. Here's 3 less than or equal to X less than 6. False, false, true, 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 false, false. Now, can you tell me what is the eventually going to be? Is eventually true at S0? True. Is it at S1? So S0, it's true. True. What about this one? True. True. Now, does the future include now?
Yeah.
So this will be what? True, false, false. So are we predicting true, 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 false, false? True, true, true. Watch this demo. True. Watch this demo. True. And now, false, false. Are we good? Is everybody with me on this? Okay, can you predict this one? Suppose these are some random sequences. False, false, true, false, false, true, false, 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 for P, right? False, false, true, true, false, false, true, true, false, false, true, true, false, false, true, forever. Now, can you tell me about eventually P? What do you think about eventually P?
Was you saying that pattern will?
This pattern. This is going to be false, false, true, false, false, true, false, 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 forever. And this is false, false, true, true, false, false, true, true, false. So Q is going to go false, false, true, true, forever. So what about eventually P? What will that be? True. Do it again. True, 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 and then false, false, false. Okay, so true, 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 false, false, false. And what about always Q? Or sorry, eventually Q? always true. My love for you is always true. So what do we see here? Eventually A. How do you interpret that? I don't get this figure for eventually A now.
I think the line just shows what A is, but not what eventually A is.
Oh, A is true at this point because it's eventually true in the future. Right. He's just talking about what its value is at point I. Because it's true in the future, it's true now. Eventually A is true at point I, even though A itself is not true. Yes, that's how to see it. Now look, you guys, eventually A is a liveness property. Right? Because it's desirable behavior. We want something to eventually happen. So what do we want? P2 implies eventually P4. So what does P2 mean? Here's an example how we use this stuff. P2 is, what does P2 mean? This is the statement that's going to execute next. Well, if this is a statement that's going to execute next, then what is P wanting to do? He's wanting to get into his critical section. So hopefully, if P2, that implies what? Eventually P4. And did you see why that's like fairness? If this individual wants to get in, eventually he will. So this is how we formalize it. Are we good? The next one is the always operator. Now, what does always mean?
Never not.
Yeah. Oh, that's a good way to do it. Well, yeah. Well, never. Well, we're going to have a theorem that's very close to what you said. Okay. So always P means what? If always P is true at state J, what does that mean? For all K what? Now and in the future, P is satisfied, or sigma K satisfies P, or P holds at K, at all, now and in the future. So suppose X is 1, 2, 3, 4, 5, 6, 7. X is greater than 4 is false, 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 true, 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 true. So what? Always X is greater than or equal to 4. What do we have? False, 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 true, 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 true. Here comes another demo. So false, because of this. And what about the next state? False, because of this. False, because of this. But now at this state, now it's true now and forever. True, 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 true. Are we good? So let's do this one. P is true, true, false, true, true, false, true, 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 true. Q is true, true, false, false, true, true, false, false, true, true, true. This is kind of parallels the other one. So what do we have about always P? False, 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 true, 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 true. Are we good? And always Q? Always false. I mean, false, false, false. Yeah. Are we good? Is everybody clear? And here's our author's depiction of always A. So here it is. At this point, from this point on, it's always true. And always is a safety property, because what do we want to say here? What did we prove last time? What was this expression, not P4 and Q4? What's P4 and Q4? P4. Yeah, they're always not in the critical section at the same time. Yeah, good. Always not in the critical section. Is everybody with me? So there's our mutual exclusion. And how about to show, here's how we would formalize this, how to show starvation free. What must we prove to show that it's starvation free? Always what? P2 implies eventually P4. That always has to be the case. And if we can prove that, we've proven starvation free. Okay, now, here comes the next little thing. Do you remember how in propositional calculus we started off by learning the truth tables? Remember that? And what is a theorem in propositional calculus? It's true in all what? In all states. And the one way you could prove a theorem would be to prove that a Boolean expression is a theorem would be to do what? To make a truth table with all the possible values of the variables. you know, and just go through and blah, 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 and do it. And that was kind of like the semantics. That's kind of like the semantics of a Boolean expression is showing. And in the same way, what we just did was like the meaning or the semantics of these temporal operators, right? But what did we do in propositional calculus right off the bat? After we learned how those truth tables worked and we got a feel for it, what did we do? We had a system, a logic system, equational. We used equational logic with axioms and theorems. And we never more resorted to what? Truth tables. Except every once in a while we would like to show a counterexample or to think about the meaning of it. You see what I mean? Okay, so in the same way, what we just got through doing was the semantics, but now these are all this is just like propositional calculus. There's no for all, there's no exist in the future, none of all that stuff. Everything now is just a simple axiom or theorem that we can prove using our propositional calculus. So in the propositional calculus that we learned in formal methods, recall that true and false are the two constants in that system. Well, in linear temporal logic, we evaluate expressions, Boolean expressions that might change over time. But because true is a constant and false is a constant, these two constants stay the same regardless of the state. So we see in this table that true always evaluates to true and false always evaluates to false. So they do not change with time. They are true constants, genuine constants. So the old technique of using a truth table, as we did in propositional calculus at the beginning of formal methods, no longer applies because you would basically need a truth table at every single state. And so therefore we cannot really use truth tables to determine the validity of a linear temporal logic theorem. And one of the meta-theorems that we used in propositional calculus was the case analysis. So if you could prove that the theorem was valid when P was true, and then if you could also prove that it was valid when P is false in those two cases, then you have proved it for any value of P. But that no longer works in linear temporal logic because you would have to, because there is an infinite sequence of combinations of sequences of trues and false, of T's and F's. And so if you tried to use case analysis with linear temporal logic, you would only be proving that the theorem was valid in two cases, namely when P is always true and when P is always false, and not for all the other sequences of T's and F's. So the bottom line is, you cannot use case analysis in linear temporal logic the same way we did in propositional calculus. So check it out, sports fans. Our first axiom is called self-dual. So we'll start with next. These two axioms define the next operator. What it says is that next not P equivales not next P. Will we ever prove theorem 1? Yes or no? No, because it's an axiom. And the next one is that next distributes over, what is this? Implies, implication. And what it says is next P implies Q equivales next P implies next Q. Are you with me? So the first theorem in this system is number 3, which is linearity, which states that next P equivales not next not P. This is a pretty easy one to prove. I don't think we'll take the time to write it down. But I think if you start with the right-hand side and with not next not P, and then in place of next not P, use self-dual, and then what you will get is not next P, and then double negation will get you to the left-hand side. So that's a pretty straightforward one. Okay. All right, now let's go around the class. Get out your equation sheets. Okay. Distributivity of next over or. This time we're going to start with the left-hand side, get it to the right-hand side. Okay, who wants to start? Somebody out there. Somebody out there in video land. Somebody from the future. Sending us a message from the future. There exists. Anybody? Anybody? Here. Okay, here, I'll give you a 3.59 implication. So who wants to start? Ray, was that? Okay, you want to start? Okay, so by 3.59 implication, next P or Q equals by 3.59 implication what?
Next, not
Yes, next not P implies Q. Is everybody clear? Actually, that was right. Actually, that's well, right. Is that work? Does that work?
Yeah, because then it would be not P or
Yeah.
Q, and then not P.
Yeah, I was just about to say we actually used double negation also, didn't we? Yeah, you're right. We used double negation. Yeah. Do you remember double negation? Okay, good deal. All right. Now what we're going to do is we're going to do it like this. We're going to go this way and then back to the room, and then we're going to go like this, around in a circle. So you're up next. Yes. Okay, hold on. 2, distributivity of next over implies will give us what? Yes, next not P implies next Q. Excellent. Okay, Shane. 3.59. You remember our old friend 3.59? We have an implication here.
Okay, so we turn it back into
Mm-hmm. Yes.
that just gets us next P or next
Not, well, I think there's one more step. I think you did too many steps in your head there. Yeah, we still have the not on the antecedent. So what would that be? Remember, it's not this or this. So what would it be? See, P implies Q is not P or Q. So it's not this or, so what would that be? Not.
Okay, so not,
Not-
next, not
Good, there you have it. Yeah, so it's not next, not P, or
next.
next Q. There we go. So it's not next, not P, or next Q. So Eva, what's next? Linearity, which is 3, and double negation. So now I mentioned double negation here. So yes, and that's it. Is everybody good? So you see how to do these? All right, just like before. Okay, Adam, you're up. Distributivity of next over and. So this looks like there's a lot of space here. So we're going to go around the room. Maybe we'll probably make it all the way around the room. All right. So what do we have here? Next P and Q equals by 3.12 double negation twice. We're going to pull a rabbit out of a hat here. So so if we do double negation twice, what's this going to look like? P and. Okay, next not P and not Q. Man, what about De Morgan?
Next.
Wait, is it going to be, oh yeah, it's going to be next, yeah, you're right. It's going to be next, what? Not. not P or not. Okay, so next, not, open parentheses, not P or not Q. Is everybody good? Okay, so Sam equals by self-dual. So go back and look at 1 on your equation sheet.
Not next, not P or next Q.
Yeah, not next, not P or not Q. Good. And Danny, by distributivity, distributivity of or over, sorry, distributivity of next over or.
Not next. Oh, not next. Not P or not next, not Q.
Wait, I think you might have had too many knots in there, but I'm not sure. I'm not sure. No, wait. So, wait. So next distributing over or, the next is going to go inside, right? We're going to leave out, and then that first, our initial knot is going to stay there. Are you with me? Our original knot, because we're saying next distributes over or.
Oh, no, no.
So say it again.
Not.
You want to pass? I mean, you can always pass.
What about?
Okay, you want to pass? Okay, Chloe?
So be not,
Not.
next, not P.
Okay, hold on. What about parens?
Oh. Not,
Not,
paren,
paren,
next, not P. And then
or,
next, not Q.
yes. So it's not paren, next not P, or next not Q. Are we getting this okay? Are we good? Okay. All right, so. Okay, we're going to take a little detour from the lecture that was recorded years ago. And so the next step that we're going to use is 3.47b, De Morgan. So we're going to take the negation outside the paren to the inside, and we're going to change the or to and. So that becomes not next, not P, and not next, not Q. But that looks suspiciously like linearity. So if we do that twice, we get the final result, which is not P and not Q, which is the left-hand side of what we were trying to prove. Now look, you guys, the rest of all of this is just, here's a exercise for the student. By the way, you don't have to do all of the exercises for the student in the packet. You see what I'm saying? I mean, if you look at the paper's online. I didn't bother to print out the whole paper. I just gave you the equation sheet. But if you look at the paper, then a lot of those are exercises for the students. I'm not asking you to do them all, just the ones that I assigned. Okay. One time I had one person do. He was doing all of it. And I thought, oh. Actually, I had somebody in a formal methods do that once. He was doing all. Oh, you mean we only have to do the ones that were assigned? He was proving all of them. Anyway, I don't think I have to worry about you guys doing extra work. All right, good deal. See you next time.